Good morning, everyone. Good morning, friends. So, first of all, welcome back to our sessions on CNN, Convolutional Neural Networks. So, in the previous sessions, we have understood the theory part, and in today's session, we are going to, work on a project related to image classification. Okay, so I'll quickly show you the data first. Okay, I'll fix the context. Then we'll actually, dive into the project. Right. So there are two classes. One class in which we have cat, images related to cat, and the other one is related to, dog. So we are going to build a CNN arc model, and this CNN model is going to classify the images. Either they belong to cat class or dog class. Right? So let me show you the data first. I have two folders in which there are subfolders of the two classes. Under the training set, you see there are two folders. One folder has cat related images and the other one has dog images. Okay, so let me open them as well. So in total, there are 4004 images in dog folder, and the similar, even the count of images with respect to cat is also same, almost 3995. So what I'm going to do is I'll take these two folders in which we have the images related to both the classes, dog class and the cat class, and we'll be building a CNN model which helps us to classify these two classes, binary class. So in short, we are going to work on binary classification related to image data, right? So friends, I hope the context is very clear. And if you are joining for the first time, ensure that you subscribe to our channel. So the reason behind is we are going to come up with the new sessions. We have a good amount of sessions that we're going to plan in the future. So in order to get notifications, I request all of you to subscribe to our YouTube channel. Okay. So, and moreover, if you are not aware of CNN architecture, okay, just go through our playlist where we have, a couple of sessions on CNN, Convolutional Neural Networks. Right. So the overall data set has 10,000 images of both cat and dog classes. Okay. So under the training data, we have 8,000 images, and under the test set, we have 2,000 images of both dog and class together. I'm talking about together. Right. So we'll get started. The first step is to import the required libraries. Whatever the libraries that are required, we are supposed to import them. So I'm importing OS module initially. Okay, so this OS module provides a way to interact with the operating system. Okay, so whatever the operating system we are going to use, so this particular module helps us to interact. So it generally helps us to read the files, the data and that. Then I'm also importing NumPy, a module which is generally used to do basic mathematical calculations, or in order to work on arrays, in order to manipulate arrays, we use NumPy module, and I'm giving an alias name, okay, as NP. Along with OS and NumPy, I would like to also import TensorFlow. So this TensorFlow is one of the open source ML framework designed by Google. Okay, so this was actually designed by Google, and this TensorFlow helps us to build and train deep learning models. Okay, so the deep learning models are generally built using TensorFlow library. And I'm also giving an alias name as TF. Then I'm importing matplotlib.pyplot. So that means I'm importing pyplot, not matplotlib, a module under matplotlib for visualization. Okay, so it's a module under matplotlib, and I'm giving an alias name as PLT. Right. Then followed by, I'm going to import Keras from TensorFlow. So this Keras is a high-level API which is available in TensorFlow and used for building models. Okay, building the models, and even for training the models, we use Keras. Excuse me. From Keras, okay, from this API, I'm just importing layers and models. Okay, so I'm not importing the Keras API together, but I'm just importing only two methods. They are layers and models. So this layers helps us to create different layers. Like we can create a dense layer, convolution layer. Like in this way, we can come and create multiple layers, multiple different layers using layers. Then models helps us to group the layers into a single model. Okay, so whatever the layers that we create, different layers that we create using layers, they can be grouped into one single model using models. Right. And finally, I'm going to import image data generator, load underscore image to array. Okay, so three methods I'm going to import from tensorflow.keras.preprocessing.image. So by this time, you should have got some understanding. So that means initially we do some kind of pre-processing, right? On whatever the data it might be, we do pre-processing. So on images, we do pre-processing, and they are generally done using image data generator. So this image data generator is generally used to do data augmentation. So augmentation techniques like rotating, flipping, zooming, then performing scaling. Okay, so all these different types of techniques can be done. Augmentation techniques can be done using image data generator. Then I'm also going to import load image. So this load image helps us to load the image, the input images that we have, right? So these images will be loaded using this load image as a PIL object, Python imaging library object. Okay, so nowadays it is called as pillow, right? In olden days, it is nothing but PIL. Okay, so it helps us to load the images into a PIL object. See, loads an image into a PIL format. So the advantage of using collab, right? Then finally, I'm going to import image to array. So this image to array helps us to convert the images that were loaded to array format. Because whenever you are going to build your model, so as part of your training, the images should be converted to numbers. So that will be done by image to array method. So I hope it's very clear. Whatever we have, we are going to import the libraries or the modules. Initially, we should have a clear understanding. Why are we importing? What is the use of each and every module should be understood. So I hope it's clear. So let us quickly execute the cell. So it's done. Then I'm also going to import um, I'm going to import drive from google.collab. So this drive module helps us to get the access to the files, to the folders that are available in the same drive. Okay, so whenever you are going to use Google Colab, this Google Colab is a cloud-based IDE, right? So whatever, you can also access your data from drives. Drive is again a cloud-based, you know, tool which helps us to store our data. So what I'm going to do is, instead of loading the data from my local machine, I would like to load or I would like to mount my drive so that I'll get the data from my drive itself. So for that purpose, I'm mounting my drive. Okay, from the module, I'm using a method called mount, and this mount helps us to, mount your Google Drive at that specified mount point path. So at this path, I would like to mount my drive. Let me execute it. You focus on the output. When you're doing for the first time, it will ask you to give necessary permissions. Once after giving the permissions, it does not ask you time again. Until unless, if the session got expired, yes, then it may ask you again. It's done. Now I'll go and define my paths for both training and testing path. Okay, so I'm just fixing my base path. So in this path, under my drive, collab notebooks, under data folder, I have both train and test. So let me show it to you, friends. So under my drive, collab notebooks, I have a folder named as data, in which we have train set, test set, and two images of cat and dog, right? So I'm going to use these two folders in which we have the data related to both the classes. Okay. So I'm just fixing my base path. So to this base path, I'll be joining the other two paths. Okay, I take the base path, and within the base path, if you go inside the base path, we have two folders, right? Train set, test set. So this train set will be added to the base path to get the train path. In the same way, we'll also get test path. Okay, so that means I'm using os.path.join function, the method from the module of path. So this will ensure to create the path for both train and test. So in short, we are defining our paths for both train and test. Okay, next to after defining our dataset paths, I'm going to fix my image size, because friends, if you observe here, let me take train set. Okay, I'll take dots. If you observe here, are all of these images are of same size? Probably not. See, some images are different size, some are, rest of the images are in different sizes. All of them are not same size. So what I'm going to do is, I'm going to adjust the size of image to a standard size. 150 height and 150 width. So I'm going to adjust the size of our images, whatever might be the image. So it should be 150 cross 150. Then next to it, batch size is also something I want to fix upfront, and it is 32. So that means per batch, only 32 images will be passed. Per batch, only 32 images will be passed. So let me execute it. Done. Fraction of seconds, it's getting executed. Now, post fixing the paths, the dataset paths, and also defining the image sizes, I'm going to do data pre-processing on images. Since this is not structured data, images come under unstructured data, right? So the data pre-processing steps differ, right? So here we have augmentation as a pre-processing step. So for augmentation, we'll use image data generator method that we have imported. Earlier, we have imported image data generator, right? So I'll be using image data generator to perform augmentation. So I'm defining two variables in which there are different types of techniques under augmentation. So let us understand. Initially, I'll perform rescaling. What is the purpose of rescaling? So if you take images, okay, so what happens? Images will be converted in the form of pixels between the range of 0 to 255, right? Yes, where 0 represents black, 255 represents white. So if you have higher values, obviously the computation becomes expensive. It's a burden on our machine. So in order to reduce the computation, it's better if you rescale the images. If you scale down the images, okay, so obviously your computation uh, becomes very faster. Okay, within fraction of seconds, it gets executed. So what I'm going to do is I'll be dividing each and every value with 255 so that all the values will be between the range of 0 to 1. All the values will be between the range of 0 to 1, where 0 represents same black, 1 represents white. Since the values are smaller, computation becomes very fast. Then next to rescaling, I'll also perform rotation as a technique, and it is 20 degrees, either plus 20 degrees or minus 20 degrees. Okay, the images can be rotated so that it creates different angles. Even though if the images get rotated at different angles, the model should learn, right? So I'm just coming up with multiple augmentation techniques over here. Then next to it, we have width shift range as 20%, height shift range as 20%, shear range as 20%, zoom range as 20%. Okay, so Y20 is, I just went with a random value, friends. Okay, you can also experiment with some other value. Okay, so what exactly happens with width shift range? So that means you have width of the image. So the width of the image will be shifted 20% either towards left or right. Okay, in the same way, height shift range. The height of the image will be shifted 20% either towards top or towards bottom. Then shear range, your image gets applied with kind of shear with 20%. Then zoom range 20%. So if you take an image, let me take this image, random image. So this particular image will be zoomed 20% or it may be zoomed out 20%. So what exactly happens is when the model gets trained on different angles, different positions of the images, it learns more, right? So the underlying patterns can be understood. Whatever might be the person, whatever might be the position of the image, it has to, classify the image as a dog or a cat. So these augmentation techniques helps us to do that. And finally, I am also keeping horizontal flip is equals to true. So that means if the image, so within the image, okay, let me take this. So if you see here, the head of the, where is the head of this particular dog? It's obviously towards the left side of the image. So when I apply horizontal flip, so towards horizontal, the flip happens. So the head will be towards, the right side of the image. So that is what horizontal flip means. So all of these are part of augmentation. They are part of augmentation techniques, right? Then In the same way, I'm also coming up with one more object in which I'm using image data generator, and this is for test data. Why? On test data, I'll just rescale the images between 0 to 1, but rest of the things are not required. They're not, the rest of the techniques are not required. So let me execute it. Done. Now, let me go and use the augmentation techniques, whatever we have used, we have defined. I'll be using them on our data. So train underscore data gen is nothing but the augmentation techniques that we have defined. Okay, where we have multiple augmentation techniques. I'm going to use it on the train path. So what is our train path? This is our train path. Okay, so on the train path, it will be applied. Okay, where the target size should be image size. So all the images will be reduced to 150 cross 150. Then batch size will be just 32. And class mode is equals to binary. So that means in this directory, okay, so we are aware that we have only two classes, either class dog, dog class or cat class. We have only two classes. So that is the reason we kept it as binary. So let me execute. Done. So it says in this particular directory, there are 8017 images belonging to two classes. There are two classes in which there are in total 8017 images. In the same way, I'll also do for test. But we are aware for test, I have to just rescale the images. Rest of the augmentation techniques are not required. So the same code, but I'll just change the path to test path, and the augmentation technique that I would like to apply is test underscore data gen. Done. How many images? It is 2023 images belonging to the two classes. So under the two classes of test path, we have 2023 images. Together, I'm not talking about one class, friends. Okay. Of two classes, we have 2023 images. Right. So far we have just completed, loading the data, then the augmentation were being done. So that means pre-processing is also done. Now let us define our CNN architecture. Okay, I'm going to define my architecture for convolutional neural network. So this is something very important. This is because this is the heart of the entire code. So try to focus. Right. So I'm coming up with a function. So this is a custom defined function, and the syntax says def followed by function name. So the function name is build underscore deep underscore CNN. Okay. So I'll follow the syntax. Indentation. Right. So I'm going to use models which we have imported from Keras, an API. I hope you remember. From Keras, we have imported models. So this models helps us to group the layers. So inside it, I have the layers. So all the layers will be grouped by these models. Okay. So I'm going to come up with a sequential model. So that means one by one next to the other. So the first block says, what is the architecture of CNN? Initially, we'll have convolutional layer followed by pooling layer. In the same way, we can have multiple convolutional layer, pooling layers. What is the purpose of convolution layer? In the convolution layer, the convolution operation takes place, right? What is the purpose of pooling layer? In the pooling layer, the number of, it is going to reduce the dimension. The output that we get in the convolution layer the output can be reduced in size by pooling layer. So in this way, we can have multiple convolution blocks. So I'm defining 4 convolution blocks in which I have convolution block 1, block 2, block 3, block 4. So let us understand one by one, friends. So as we discussed, layers that we have imported from Keras are used to create different layers, right? So layers dot convolution 2D. Okay, so it is going to create a two-dimensional convolution layer in which there are 32 filters. This 32 is representing number of filters. Okay, then followed by size of filter. So each and every filter will be of size 3 by 3. So that means 9 values inside this filter, right? So 3 by 3 filter of 32. So there are 32 different filters of size 3 by 3. Then followed by activation function that I would like to go with is ReLU, rectified linear unit. What is the help of activation function as part of convolution operation? This activation function, especially ReLU, introduces some kind of non-linearity into the neural network, as well as, it also reduces the negative values to 0. So wherever you get negative values, those negative values will be reduced to 0. Why? ReLU works on the function max of 0 comma x. So wherever we have a value for x greater than 0, obviously x value will be written. Whereas if the value of x is less than 0, obviously 0 will be written as output, right? So activation function helps us to add some kind of nonlinearity into the neural network, as well as it also reduces all the negative values to 0 from this output. I mean, as part of the convolution operation, you get the output. So in the output of the convolution operation, if there are negative values, they'll be reduced to 0. Simple. Clear? Then what is this? Input shape. So initially you'll have input layer, right? So in the input layer, you will have the size of the image as 150 cross 150. And what is this 3 representing, friends? This 3 represents number of channels. Why 3? Friends, what kind of images are we going to use? Are they grayscale images? Is it grayscale image? No. All of these are colored images. So obviously they belong to RGB layers. So as part of theory class, we discussed types of images: grayscale image, RGB image, red, green, blue. So 3 channels. So these 3 represents obviously the number of channels. So that means input images will be of size 150 by 150, okay, of 3 channels. What are those 3 channels? RGB, red, green, and blue. So this particular line is talking about the convolution operation. Initially, 32 filters of size 3 by 3, okay, will go and work on each and every image of size 150 cross 150 cross 3, height, width, and channels, right? Then once convolution operation is done, we'll also perform pooling operation. Will obviously the output of convolution layer will be passed to pooling layer. This pooling layer helps us to reduce the dimension. It helps us to reduce the dimension. Okay. So from the same layers, I would like to create a pooling layer. And what kind of pooling I'm going to use? Max pooling. So that means the maximum value of the region will be given as output. So max pooling of size 2D, so two-dimensional. Okay, only rows and columns you'll have, and 2 cross 2 comma 2 is representing the size of your kernel. So a 2 by 2 kernel, a filter will be taken, and that will be used on the output of convolution operation output to get, the features reduced in size. That's what, if you understand these two lines, then the rest of the blocks are same. Then what is the purpose of rest of the blocks again? If you see here, what I'm doing in block 2, is it the same code? Yes. But number of kernels got increased. What about block 3? Same code, but again, the number of kernels is what? The number of filters is what I'm increasing. Block 4, again the same. So this actually helps us to, reduce, as I'm increasing the number of filters, this helps us to, identify the complex patterns in the images. Okay, it helps us to identify each and every complex patterns, the underlying patterns in these images. That is the purpose of, uh, that is the purpose of the increase with the increase of filters. Why am I increasing in size of images is, this is the actual reason. Once after completing the convolution and pooling operation, now I'll go and flatten the output that we get here gets flattened. That means the two-dimensional output will be converted as a 1D vector using this flatten function. Okay, then it starts building dense layers. Okay, so then it starts building dense layers. So within the first dense layer, you'll have 512 neurons, and the activation function that you are going to take is ReLU. And the activation function that we want to take is ReLU. Okay, so all the values that you have in the flattened layer will be that will be connected to the neurons that are present in this dense layer. Then we also have dropout. So this dropout helps us as a regularization parameter, where 50% of the neurons in this dense layer gets randomly, 50% of the neurons get dropped out. Why? Because time again, if the same neuron gets active and if they are getting, if they get same amount of learning journey, they cannot understand. What about the rest of the neurons? So that is the reason, we have to use dropout function, this dropout parameter, which helps us to reduce the overfitting of the model. And moreover, it ensures that each and every neuron present in that layer to learn the pattern. Not every time the same neurons has to be learned. And finally, in the output layer, you'll have only a single neuron, okay, where the activation function is sigmoid. Why sigmoid? Because this is a binary classification task. So you should get either the output as cat or dog. So sigmoid, what is the formula for sigmoid function, friends? F of x is equals to 1 by 1 plus e power minus x. Right? So when you use sigmoid activation function in the output layer neuron, this will give the probabilities ranging between 0 to 1. So we'll define the threshold. If the value greater than 0.5, so that means cat. If the value is less than or equals to 0.5, the output should be dog. So we'll define the thresholds that we'll do later. So this is the complete architecture of our neural network. I hope it's making sense. So probably you may not understand when when you don't have any knowledge on the theoretical part of CNN, and if you're directly listening to this use case, okay, probably you may not understand. My sincere request is go back, and listen. First, initially understand the concept of CNN, then your understanding with respect to the use case will enhance. Okay, because what is convolution operation, what is pooling operation, okay, what is stride, what is padding, everything we have covered, friends. Okay, in case if you have missed, go and quickly recap, go and listen to the sessions of CNN. And finally, I would like to, once after the model got created, I'll use compile function. Okay, this compile helps us to compile the model. Okay, whatever we have defined over here, using the optimizer as Adam. So under tf.keras.optimizers, one of the widely used optimizer, Adam. Okay, so this Adam will be used as an optimizer with the learning rate as 0.001, 0001. Okay, this is the value of eta, right? And the loss that I would like to keep is, since it is binary classification, it will be binary cross entropy. It will be binary cross entropy. And the metrics that I want to consider is accuracy. So this will compile the model and finally it returns the model. That's it. So let us quickly execute this. Done. Now we have the function in which the entire network has been, built. So this particular function, I'm going to assign to a variable its model, and the model dot summary function will return us a table which gives us layers and the output of the shape. Okay, what is the output from each and every layer along with the parameters. That will be done by summary function. Let me execute this. Models is not executed. It is done probably. Just give me a minute, friends. Done. Yeah. Because of, I'm taking too much time, right? So it got disconnected. That's okay. See, what is a first layer? It's a convolution operation. When you take a convolution layer, within the convolution layer, the output after the convolution operation is this much. How come, Akhil? Can you please explain this? Just if you understand for one layer, obviously the rest of the blocks is very simple. There is nothing here. The only mantra that I can tell is the concept. If you are clear on the concept, you can understand all the output. So if you remember, in the convolution operation, we discussed a formula. How can you understand, or what will be the output of convolution layer? How can we fix the dimensions? Is n minus f by n minus f plus 1. So if you see here, what is the n? It is 150. N represents size of your input image. Then F represents size of your filter. So N minus F. 150 minus 3 is 147 plus 1. It becomes 148. 148, 148. Then Y32, Akhil? 32 represents number of filters. Number of filters. See. Okay, so this is the output of first convolution layer operation. Okay, then you can also calculate the parameters. How many parameters you'll have? Since I'm going to have a 3 by 3 filter, and this 3 by 3 filter, you're going to work on a RGB image. So 3 class 3, 9. Again, 9 multiplied with 3, 27 plus 1. 1 represents the bias. The bias that we add at each and every case. So 28 multiplied with 32. If you multiply 28 and 32, obviously you should get 896 as parameters. Simple. The logic is very simple. Okay. In your mind, assume the architecture of, convolution operation. Okay. Assume the entire architecture in a single go. We have four convolutional blocks, block 1, block 2, block 3, block 4. So in each and every block, we have convolution operation followed by pooling operation. Then convolution operation followed by pooling operation. So in this way, you can calculate the number of parameters. Then when it comes to pooling layer helps us to reduce the dimension. So from 148, it is becoming 74. The size of the image becomes 74 cross 32. 32 is number of filters. Okay. Why it became 148 became 74 is we are using a 2 cross 2 filter as part of pooling layer. So what happens? Just divide by 2. So it is 74. I hope it's making sense. So friends, again, I'm mentioning here, if you haven't gone through my sessions on CNN, do watch them. Only then you can understand the concept of this code. Probably this code will be clear only if you, complete the sessions. I hope it's making sense. In this way, if you see at the end of final pooling layer, what is the size of the image? 7 cross 7. 7 cross 7. Right? So in the same process, you can calculate the parameters. And finally, in the output layer, you will have only one neuron. Okay. So obviously, the parameters you're supposed to add. 512 plus 1, 513. Right? So this is what summary function gives you the entire table so that we can quickly understand what will be the output at each and every layer. At the end of each and every layer, what will be the output and the number of parameters can be understood using summary function. Right. Now I'll start the journey. So this is where we train our model. The model gets trained here. What am I doing? I'm taking the model. This model I'll fit on the train generator. What is train generator? Train generator is nothing but in which I have my entire train data. The entire train data is what I have in train generator, and epochs I'm adjusting them to 10. So what is an epoch, friends? Epoch is nothing but the number of times you're passing your entire data through the neural network. So through this neural network, how many times you're passing the entire data is what a epoch means. So I'm just keeping the number as 10 depending on the number of images. Okay, depending on the size of your data, you define your epochs because this may, kill your systems as well. If you are using CPU machines, okay, it probably make your machine stop because in our case, we are going with big data. I mean, the number of images are very big. So probably I have adjusted the runtime to GPU. Okay, so that is the reason you better go and use Colab. Google Colab is what I suggest, right? So I'm keeping the epochs to 10 and the validation data, I would like to keep it as test generated. So once after getting trained, let it also get validated on the test data. So I'll start. Okay, it's getting, I have to do it again from here because of too much time, It will ask you permissions like this, friends. When you're mounting your drive, okay, it will ask you permissions. Only then the drive gets mounted, and you should get a see, you should get a successful message like this, mounted at this path. So to this path, you'll see your drive. See, this is what my drive. So under my drive, so this is where under content you have drive, right? Under drive, I have my drive. So drive got mounted. See, collab notebooks. Then under data, I have test, train, and the images. Anyways, I'll do it again. I'll quickly make it fast. So friends, I would like to suggest you guys to use Collab. The main reason is, if you are using images, if you're working on image related data, it's better you go and use Collab. The main reason behind it is when you start your epochs, when the model gets trained, so during the training journey, until unless if you use a GPU machine, okay, that's okay. But if you're not using a GPU machine, your machine gets hung. So my sincere request is use Collab. The journey got started. So here we can see the epochs, how much time it is going to take. Everything will get a you know clear in understanding about each and every epoch. So I just started now. We'll see. You see, epoch 1 by 10. That means so this is the first epoch out of 10 epochs. It is showing you the estimated time. It is calculating the accuracy, train loss. Sorry, this is not the loss. It is talking about this one, binary cross entropy. Yes, so we are done with the first epoch. You see how much time it took for the first epoch itself. Okay, 1 to 5 seconds. And per step it is 5 seconds. Okay, the accuracy that we have got is 53% and the loss is 69. Okay, so this is on train data. On the validation data, we also have the accuracy and the loss. But from here onwards, the journey of the epochs it will be a bit faster compared to the first epoch. See, let's see. So friends, you see here, we are done with the 10 epochs, and one change that you're supposed to observe here is as the number of epochs keep on increasing, the accuracy is also got increased from 53% till 75%. Right? Now, considering this final result, the train accuracy that we have got is 75% and the validation accuracy is 79%. So almost they are close. Right? Now I would like to plot the accuracies and the loss graphs with respect to both train as well as validation. Here is the code, and this is how we can see the accuracies compared with respect to training and validation. Okay, so on the x-axis we took the number of epochs 0 till 10, and on the y-axis we took accuracies. The blue color line indicates train accuracy and the orange line indicates validation accuracy. So as the number of epochs got increased, even the validation and the train accuracies got increased. Right? Yes. On the right hand side part, we have one more subplot. So where we are going to compare the loss. Okay. The same x-axis I'll take epochs and on the y-axis I'll take loss. Okay. So with respect to the number of epochs getting increased, the loss got decreased with respect to both training as well as validation. For both training and validation, the loss got decreased. Now, I would like to build a function, and this function will predict whether the passed image does it belong to a dog class or cat class. Okay, so this is the function, a custom defined function is what we are defining here. Okay, so the load image initially takes the image, the path that we'll be initially passing, and gets converted to the same standard 150 by 150, both height and width. This will be rescaled. It gets normalized, dividing by 255. Okay, once after the image got divided by 255, we are going to pass the array. This array will be passed and the model gets predicted. We'll get the predicted value here. So if the prediction value, if it is greater than 0.5, we'll predict as dog. If it is less than 0.5 or is equals to 0.5, we predict as cat. See, done. We are done with the function. Now I'll use the function and I'm passing a dog image. Okay, this was already loaded inside the files. So I'll just execute. Let's see whether we'll get a dog or not. Okay, so I have to do it one more time because the data got missed here. Let me upload two images, both cat and dog. So done. Now let me rerun the code. So the past image is dog, and even our model is also predicting it as a dog class. In the same way, let us parse a cat, image of a cat, and let's see. The output is again the same. So the model is performing well, but the challenges that we have observed is, the training journey. So with respect to the training journey, as the number of epochs are more and even our dataset size is also huge, it took a lot of time to train the model, but the output is, very good. The model is predicting the class as it is, right? So in this way, CNN helps us to do multiple tasks related to images. We can perform detection. We can also perform classification, segmentation. There are n different types of, use cases of CNN, right? So I hope we have learned a new topic today. Okay, so if you feel the same, ensure that you give a like to our video before you leave. Also share across your connections. Ask them to learn CNN because this is one of the basic fundamental topic under artificial intelligence. Right. So that's all for the day. Again, we'll meet in the next session. Until then, take care. Have a great day. Signing off. Bye.